Okay, so we want to continue from yesterday with our approximate integration. And unfortunately, it seems like we're starting to get a little behind. Not too much behind, maybe like a quarter of a day, but I don't want it to like snowball and have us start to get even more behind, especially with today being a recitation day. So I kind of want to get through this a little quicker in terms of approximate integration. I'm actually going to skip deriving some of these formulas and just talk about it and skip a little bit of the notation. The sum notation, if you guys haven't seen it yet, it's going to be completely foreign. You're not going to know what the summation notation is, and it's going to be something that we want to touch base on. I'll give a little bit better explanation on how we use and how we manipulate summation notation once we actually start sums and series. For now, with approximate integration, the most important thing is the algorithm. You have to kind of just know the process of how to do an approximate integral. And then you also have to know how to use the formulas for the error bounds. So, real quick, let's draw this picture we were drawing yesterday. Let's draw two pictures actually, because it sounds like you guys already have done the left hand and right hand rules. So, we kind of wrote that down, and I wrote sort of when we make these tables, the table of values for the function. You always use starting with number zero, starting with zero, all the way up to the second to last term for the left hand rule. And then for the right hand rule, you leave off the first one and use all of the terms on the right as your y values. We want to learn the trapezoid rule and the midpoint rule. The midpoint rule is kind of a pain. So let's do the trapezoid rule first. So we've got these partitions that divide up the interval from A to B. And we saw, drawing the pictures with the left and right, where the boxes lie. Of course, you can eyeball and see where left and right are over and under approximations, depending on the shape of the curve. And so the question is, can we improve upon that approximation method? Instead of having this overlap and this overhang, can we get this sum to converge faster, so to speak, to give a more accurate representation of what the area is without adding too much more complexity? And so the idea is, well, instead of drawing a box between the two endpoints on our partition, we're just going to draw a straight line between each of these. And so what you should notice is that one of these boxes, if we turn it sideways, what do we get? Looks something like this. And that's a trapezoid. So the two vertical lines, we actually need to turn it sideways because those two vertical lines are actually our bases. They're parallel. And then the other two sides doesn't really matter if they're parallel or not. One of the important things, though, is that we do, of course, have right angles, which means this side here is our height. So that is our delta x coming from the width of our partition. And then this one, let's see, which way did we turn it that way? So let's call this f of xi, f of xi plus 1. And then you just have to remember that the area of the trapezoid, think of the area of a triangle, except the top of a triangle has a width of 0, right? The two lines come to a point. So what we want to do is just average the bases to the bottom plus the top width times the height. So it's essentially 1/2 base times height, except it's half the bases, half the sum of the bases times the height. And so the thing to notice is that aside from the first and last partitions, all of those trapezoids, or at least each of the sides of the trapezoid, are going to be counted twice. So in this first one, we're going to do 1/2 f of a plus f of x1. And that'll give us the area of this trapezoid. The next one, we have to do 1/2 f of x1 plus f of x2. So we're getting an extra f1 in there. So our formula is going to look like this. The area is 1/2, and it's going to be 1/2 base times height for all of these. So when I add each one together, we can factor out the factor of 1/2 from the entire sum. We can factor out the factor of h from the entire sum. So it's going to be 1/2. H is given by delta x times the sum of f of x naught, which is f of a, plus, and then we're counting each of all the other ones twice. That's our formula. What is it saying? We just want to add up. Let's take a look actually at our left and right hand rule. Let me write out the summation notation first. So our summation notation is 1/2. I don't know if we can even write that well since we've got 2's and all there. We want to do f of xi. I equal to 0 to, here, let's write it out a little differently. We will have the sum of I equals 0 to n minus 1 f of xi plus equals 1 to n f of xi. So if you're familiar with summation notation, this will make a little more sense. And then we are taking half of that times delta x. In other words, what this is going to end up being is the left-hand sum plus the right-hand sum divided by 2, so average of those two, and then times the width. Let's do an example. It'll make more sense when we actually see a table. So let's draw out a table of values here and just go through the process. I think the process will make more sense. This is one of those things that, like, once you do it, you kind of just, that's what you need to learn, is the process. The notation for something like this, if you're not familiar with summation notation, isn't going to make much sense. So we've got our x values and our f of x values. Now, I highly recommend, if you've got to do one of these by hand, always make a table. They can always give these to you in different formats. We could actually give you the formula of the function, you know, f of x is equal to square root of 1 minus x, or something like that. Or we can give you a graph of a function, and you have to, from the graph, pick out the values of f of x. The easiest way to start it, in my opinion, though, is always to make a table. So whatever version you're given, start with a table with the values that you care about. So our x values, let's just go 0 to 10. And then let's plug in some f of x values. And unfortunately, I was looking at some of your homework assignments. It looks like for some of the web assign, they actually do want you to do n equals 10, meaning a partition, 10 partitions for some of these sums. So it's kind of annoying. You're definitely going to need calculators for these web assign problems, especially if they give you formulas for functions like e to the x, where you have to compute by hand. I know it kind of defeats the purpose of doing things by hand and doing these approximations when you're already using calculators, but the big idea, I think, is to teach you guys how the computers are doing it and to get started on programming it yourself. So if you've got programming experience, coding these up in like a nice Python script or something, good practice. Okay, so how do we do the trapezoid rule? The problem will usually give us the number of partitions. So the problem we have, how many numbers do we actually have here? We have 10, or excuse me, 11. There's 10 partitions. You just have to remember that each of these is an endpoint. So you kind of have to think with the right-hand sum and the left-hand sum. Left-hand sum, we're using the left-hand values. So the first 10, 0 through 9. The right-hand sum, we're using 1 to 10 for the right-hand endpoints. Trapezoid rule, we need to use all of them. And then midpoint rule, we'll have to do something a little different. Midpoint rule's a little odd. So let's say use trapezoid rule. With n equals 10 to approximate the integral. So some things that are nice to write out. If n is equal to 10, you want to figure out your delta x. Of course, we have all of the values there. Our a is 0, our b is 10, and it's not too hard to figure out that our delta x is going to be 1. So, of course, our formula for delta x, I'm not sure if I wrote it down yesterday, but just to write it down again, the width of the interval divided by the number of partitions we want to take. And then, of course, the other thing to write out is the formula for it, for our trapezoid rule. So we want to take one half delta x we want to multiply all of the middle terms, so all the middle y values, by 2. And then essentially just add on the endpoints. Alternatively, you could do the left-hand sum and the right-hand sum, and then divide by 2. So plugging those in the formula, all of our values now, not too difficult, just kind of a lengthy computation. So our delta x was 1, our f of x 0, we're going to have minus 2 plus 2 times minus 1 plus 2 times 1 plus 2 times 3 plus 2 times 7, 2 times 11, 2 times 11, 2 times 10, plus 2 times 8, plus 2 times 4, plus 2 times 1.
Isn't that just 1?
Say what?
That's the last term.
Sorry, what'd you say?
Isn't the last one just 1 because it's the last term, not multiplied by
Ah,
2?
yep, thank you. Plus 1. And then the challenge is adding all of those up. And I've actually looked at some of the homework problems. It's like they're decimals. They want you to compute like a partition of 10 with decimals. So you got to use a calculator for this, which is a skill in and of itself. So how do we do this quickly? Well, we can kind of factor things out a little bit. So we have 1/2 times -2 plus 1. So this is our first and our last. Plus, now the 1/2 times the sum of all these middle terms. The 1/2 and these powers of 2 are going to cancel. So that'll save us a little computation. Then we got -1 plus 1 plus 3, 7, 11, 11, 10, 8, 4. And so this term, -1/2. And now let's add these guys up. We got 0, 10, 20, 42, 50, 54. So 54 -1/2. Not the best answers. I'm just going to go ahead and use decimals. 53.5 instead of making that a fraction, since fraction would be really ugly. Everyone follow that? Okay, so I'm going to keep the same page since I want to use that same table. Midpoint rule, let's talk about that real quick. It's different. And it can be more annoying because sometimes if you're given a table or to make the table, you often have to you're including values that aren't traditionally used on your right hand, left hand, or trapezoid roll. You're using the midpoint of the interval. So if we have a similar picture of our graph, if we take our partition like this, what we want to do for the midpoint rule is instead of using the left hand, the right hand as a height, we still want to make boxes. But what we want to do is pick the middle of the interval and then make a box through there. Pick the middle of this interval, find that height, and make a box through that height. And we keep doing that. Middle of the interval, y value, box through that height. And so you can kind of see the nice thing about the midpoint rule is no matter what the shape of the curve, there's usually a little bit of overhang, but also a little bit of underhang, right? Each of these boxes are under the curve a little bit and also over the curve a little bit. So the over and under combination sort of cancel each other out. And this gives a really good approximation. It's actually the most precise approximation for the same number of partitions. The problem is the formula, or the problem is, I guess I should say, the formula is the formula. It looks similar to all the other ones, is that sometimes you have to find these extra points and compute them. So the formula is the same. It's going to be just base times height for the area of the boxes. And since the width is delta x, going to look like this. F of x1 bar plus f of x2 bar where xi bar is equal to xi plus xi minus 1 over 2. So whatever ith x value you have, that one plus the previous one divided by 2 gives you that midpoint. That's our average x value in that interval. Plug that into the function to find the y value. And then, of course, multiply by the base to get the area of each box, and then add them up. So that's all the midpoint rule is. And so let's go back to our table here and take a look as to how we can do a midpoint rule approximation with this. So unfortunately, because of midpoint, if I use my delta x, or if I said n was 10, what's our problem? Well, here's my 10 intervals. What's the midpoint of each interval? Well, between 0 and 1, the midpoint is a half. Do we have a y value at when x is a half? No, we don't have it. 3 halves, we don't have. So we can't use a midpoint rule. At least we cannot use a partition size. We cannot use 10 partitions for the midpoint rule given this table. What we can do, or what we would do instead, is to say something like use midpoint rule with, say, n equals 5 to approximate the area. So let me color code the notes a little bit. We'll use green for these midpoint rules. So let's go back up here. Actually, here. Let's do our computations real quick. So if our n is 10, our delta x, oh, sorry, our n was 5. Our delta x, b minus a, over n, is 2. So if our delta x is 2, that means our endpoints are here. And of course, what's the midpoint of each interval? So the y value we want to use to approximate the height of that box are going to be the odd numbers. And of course, we got 5 of them. So the endpoints actually don't really matter for our midpoint rule. We're only going to use these midpoint y values, and then our delta x is 2. So our area is going to be delta x times the sum of those y values. So let me write them down. We've got -1 plus 3 plus 11 plus 10 plus 4. So add them all up, times 2. Basic arithmetic here. What do we got? So 2 and 11 is 13, 27, 23, 27 times 2. And look at what we got. Actually, a really close answer. So I kind of just made up these numbers from the examples, and we can see as we compute, even if I take a more terse partition size, right? Broader partitions with a midpoint rule. Midpoint rule still gives a pretty accurate answer in terms of taking even finer partitions with the trapezoid rule. Any questions on that? So the process is the most important thing. I would just say, like, in terms of using the midpoint rule, if you're given a function or if you're given a graph, the midpoint rule, you're not going to be given the table from the get-go. So you can essentially just make your table with the values of the x value as the midpoints of each partition. Or you may want to make, I don't know, you may want to make two tables depending. Like if it helps you to do a midpoint rule, if they give you a graph, I can draw it out. Like if we're given some graph of something like, let's just do an easy function like x squared. And let's say we are on, let's just do something like 0 to 5. And if we want n equal to 5, midpoint rule, it might be helpful to just kind of list that out and, you know, do all your computations. Our delta x is 1, but that's going to make your endpoints 0, 1, 2, 3, and 4, and 5. And so when you start your table, you would do the average of those, the midpoint of each one's. So you would have 1/2, 3/2, et cetera, et cetera. And then once you have your midpoint x values, plug those into the function to find the corresponding y values, and then plug them into your computation. Of course, trapezoid right hand or left hand, once you have the endpoints, you use those for your x values. Back to the formula page. We had requests. Let's see. Go to formula page for midpoints or trapezoid. So this is our midpoint formula. In summation notation, it's just f of xi bar times delta x I, or just delta x since they're constant. All good now. Cool. Okay. So we've got about 10 minutes. Let's try to do some of these error bounds. We might have to use a little bit of time tomorrow to do the error bounds. As we kind of just saw, not too tricky, right? There was nothing really complex there other than the length of the calculations. If you want to take bigger and bigger partitions, doing it by hand really sucks. So it is an exercise in practicing technological skills to help you with some of these calculations. The error bounds, though, can be a little tricky. I know a lot of students in the applied math, or excuse me, the math department struggle with a lot of these error bounds. And let me pull up the formulas here. Here we go. And let's see, I don't have the right and left hand. Midpoint rule. error bounds. Let's find those real quick just to keep them all together. Well, I'm not finding it. It's in an older section of the book. Let's cover the midpoint and the trapezoid rule. I don't know if the left and right hand rule are going to come up in this section. So our error bounds, we have, suppose that the derivative and we need the, I think, third derivative? No, second derivative. So suppose that the second derivative is bounded by a constant on some interval, the interval we want to approximate. Then the errors in the trapezoid and midpoint rule which we denote by ET and EM respectively, are given by so our trapezoid rule, the error is bounded by that constant times the width of the interval cubed over 12n squared. The midpoint bounded by the constant times the width of the interval cubed divided by 24 n squared. So what is this saying? This is saying that the concavity of the function, the second derivative, dictates the amount of error in our approximations, as well as, of course, the size of that. And we can kind of see that for the same number of partitions, for the same function with the same bound, that the midpoint rule is smaller. The error is a bit smaller. Okay. So let's try to do a problem. I think some of the problems in the book, I was looking for examples with this. And again, the examples are kind of hard to do in lecture because they use a lot of like decimals and approximations. Let's try to find a reasonable function. Here we go. So we want to do 1 over x. That's a pretty reasonable function. Not too difficult. In terms of computations, we won't get crazy decimals. We can still use some fractions. And let's say, how many partitions? To use. So that's the approximate integral. is within 0.000001 from the true value. So this phrase here, you'll see this a lot, and we see it a lot in statistics. I don't know if any of you guys have to take a statistics course. It'd be really helpful, especially if you want to go into data analysis. Anytime you see this phrase is within, this is our error. So that's going to be what our error is equal to, or less than or equal to. We want to set our error less than that. And we can do both midpoint and trapezoid. So let's do one. Maybe we'll start with the other one tomorrow, just to see some of these error bounds and error formulas fairly quickly. So how we want to set this up, our function is the integrand. Right? We want to find the area under 1 over x on the interval from 1 to 2. And so what we need in the formula for error bounds, we need to bound the second derivative. So our first derivative is minus 1 over x squared. Second derivative is positive 2 over x cubed. And we also want to bound the absolute value of it, right? We want a positive bound. So if we needed to, if there were some minus signs hanging out, or if the interval was potentially negative, we can throw in absolute value signs there. Interval's positive, this function is positive, so it will be positive. And so what we want to do is on this interval, what's 2 over x cubed look like? 2 over x cubed, shape-wise, isn't going to differ much from 1 over x. And so if we're on an interval from 1 to 2, where's the upper bound going to be? On the left-hand endpoint. So we want to find an upper bound. Easiest technique is going to be graphing, visual. We've had enough experience now at this point with Calc 2. You've been through Calc 1, so you understand rates of change. Hopefully you understand what graphs of something like 2 over x cubed look like. And we could simply make graphing or visual arguments to say that because this graph function is decreasing, that the max of f double prime is at x equals 1 on the interval. Now, keep in mind, sometimes the graph and the function may not be that nice. It might have, on the interval we're trying to integrate, it could go up and down, right? So sometimes you have to use Calc 1 techniques. Where you find local max and mins and compare it to the endpoints, the values of the endpoints of the second derivative. So of course you would have to take a third derivative, figure out where that is 0. If it has any zeros within the interval that we care about, find those as whether they're max or mins, and go through that whole process. This one, not too bad. We know where the max is at. And then so our k value is going to be f double prime of 1. Which is, of course, just 2. So now we want to plug that into our formula. So let's write it out on this page. I'll need another page and we'll continue. Let's start with our trapezoid rule. The way you set this up, we know that the error is always less than k, which is 2, times b minus a. So we will have 2 minus 1 all over 12 n squared. If I know that the area or the error is less than this, if I take this value and set it less than the error bound that we were given, then we have a string of inequalities, and I know that the error will automatically be less than this if we solve this right side inequality for n. So we've got this equation that we got to solve. I'm going to go ahead and write it out. So of course we've got 2 over 12, which is 1/6 n squared in the denominator. Doing these by calculator, of course, you can get the numbers. General rule I follow, if a problem gives you decimals or has decimals in the problem, it's fair game to use a calculator. So feel free to use a calculator. Since I don't have one handy, numbers are easy enough. That's just 1 over 10,000. And so cross multiplying, we multiply the 10,000 over 10,000 over 6, less than or equal to n squared. And then solve that out. So what do we have? 5,000 over 3 is less than or equal to n squared. Square root both sides to find the answer. Okay, so let's start recording again. So you guys saw this, setting up the formula?
Yeah, that's correct.
Cool. So we set up the formula. We want to just solve this right sign for n. So the arithmetic, not too complicated here. 1/6 over n squared. General rule, if you have decimals in the problem or if the problem statement uses decimals, feel free to use a calculator. I can go ahead and write it as 1 over 10,000. Cross multiply, essentially. Multiply the 10,000, multiply the n squared, and then just solve the remainder of that. So when it blipped out, I did take a look and plug that into Wolfram Alpha. And we get like 40.82 is less than or equal to n. So since n is an integer, our solution for this would just be 41. We would use 41 partitions. And again, if you guys are good at coding this and can code 41 partitions and have it compute it for you, this is an integral we know how to do, right? We can actually integrate 1 over x from 1 to 2, find the actual value, take 41 partitions, and see if it's within 1 over 10,000 of the correct answer. All right, any questions?